Hi, welcome to this module, and in this module we will look at analog to digital converters. So, what are types of ADCs and how does it function? Okay. So, there are four basic types of ADCs that we will look at. The first one is called flash ADC, then we will talk about sigma delta, followed by dual slope, followed by successive approximation. So, let us see flash ADCs. The flash ADC or the flash method utilizes comparators that compare reference voltages with the analog input voltage. When the input voltage exceeds the reference voltage, a high is generated. Comparator is not needed for all zeros condition. We will see in the next slide how the circuit looks like. In general, 2 raised to n minus 1 comparators are required for converting a n bit code. The advantage here is that it provides a fast conversion time because of a high throughput, and the disadvantage is large number of comparators are necessary for a reasonable sized binary number. For example, if you see this circuit, you can very easily see how many comparators are required for 8 bit converter like C1, C2, C3, C4, C5, C6, C7, 7 comparators, right. So, this is how it actually works. So, you have a reference voltage, you have an input from sample and hold circuit, and depending on the reference voltage and input voltage, if the reference voltage is higher than input voltage, then you have 0 at the output. If the input voltage is higher than reference voltage, you have 1 at the output, and that goes to the priority encoder, and that is finally converted to your parallel binary output, right. So, there are enabling pulses to the encoder, there are op-amp comparators, and there are input from sample and hold. Let us see here. So, the flash method utilizes comparator that compare reference voltages with analog input voltage, like we discussed. When the input voltage exceeds the reference voltage for a given comparator, a high is generated, right. So, input voltage, because it is connected to the non-inverting terminal, so high will be generated or 1 will be generated. The reference voltage for each comparator is set by the resistive voltage divider circuit. You can see here the reference voltage. So, this is nothing but a resistor R1 and R2, and if you apply voltage, the voltage divider circuit. So, same way you keep on dividing the voltage until here, and that is how the reference voltage are set. The output of the comparator is connected to an input of 8 bit primary encoder. This is a primary encoder which is 8 bit or 8 input primary encoder. The encoder is enabled by a pulse, and a 3 bit code representing the value of input appears on the encoder's output. Here is the output that is appearing at the encoder's pin 1, 2 and 4. The binary code is determined by highest order input having a high level. Now, assume that the step size of 1 volts, the voltage divider sets up a reference levels from each comparator, so that there are 3 levels corresponding to 1, 2, 3, 4, 5, 6 and 7. The analog input is connected to other input of each comparator. Now, you understand this question. So, with analog input less than 1 volt, all 7 comparators will be low. What we are saying is, if you have step size of 1 volt and the voltage divider is set for all comparators, so it is 1, 2, 3, 4 until 7, then what will happen if the analog value, that is the value from the signal, is less than 1 volt, what will happen? All the comparators would be low, right. So, output will be 0. Suppose the analog input is between 2 and 3, then comparator C1 and C2, right, will be high, and the priority encoder will respond to high of C2 and produce a binary of 0, 1, 0. So, this is how the comparator works. This is how in general your flash ADC will operate, and if you want to determine the binary code output of 3 bit flash ADC and the encoder enable pulses are as shown below, then assume V reference voltage equals to 8 volts. If you have this particular signal, right, you can see here there is an analog signal and there is an enable pulses. So, suppose you are asked that the resulting digital output sequence is 100, 110, 111, 110, 100, 010, 000, 001 and so on until here. Waveform of the resulting digital output sequence, draw it. So, it is very easy. If you really see, you have to draw pulses, and for each pulse you have to show a particular signal. For the first pulse, what is it? 100. So, if you have here 3 bit flash, right. So, you have D2, D1, D0. So, 100 is given by D2, D1 and D0. So, 100, right, 2 raised to 0, 2 raised to 1, 2 raised to 2. So, 100 will give us 4, right, that is here. Now we have second pulse. So, so when you have first pulse only D2 should be on, D1 should be 0. Second pulse is 1 1 0 1 1 0, that means D2 and D1 should be on, which is right over here and D0 should be 0. Third pulse is 1 1 1. So, all three signals 1 1 1 should be high. 4 pulse is 1 1 0. So, it will be 1 here, 1 here and 0 here. It is very easy to draw. Very easy to draw the waveforms of the resulting digital output sequence. So let us see the how to design a flash type A to D converter. We have seen ADCs in the theory, we have also seen D to A converters in theory, but now let us see how, if you want to actually implement a flash type ADC in experiment, how you can implement this particular circuit. So the aim of this experiment is to design a flash type A to D converter, and of course we are using operational amplifier. The circuit is right over here, we can see it. Now the process of taking analog voltage V analog and converting it to a digital can be accomplished in several ways. We know it, right, which is called ADCs. One of the simple ways is by parallel encoding, also known as flash converter. In this method several comparators, you can see comparator 1, 2, 3, 4, you can have n number of comparators and it will be n type ADC, but we restrict it to 8 bit ADC, 12 bit ADC. So we will use we can have different kind of ADCs, like I said 8 bit ADC, 12 bit ADC, right, but the one that we are showing you here is a 2 bit ADC. So we will discuss this thing in detail, right. In this method several comparators are set up, like you can see here a different voltage reference level VA, VB, VC, VD, which you can see here, we can have different voltage here, right, and the comparators operate in such a way that if the analog input is greater than reference voltage, the analog input voltage which is here, reference voltage which is here, then if the analog input voltage is greater than reference node voltage, the comparator output will go high, right. If this goes higher than this value, comparator is high. If this one is lower, that means the inverting terminal is higher than non-inverting terminal, or non-inverting terminal is lower than inverting terminal, output will be low, right. This is how it works. This is, we already have seen the operation of a comparator, right. So that is what we said, that comparators operate in such a way that if the analog input is greater than reference node, the comparator output will go high, and it can be represented by logic 1, while if the analog voltage is less than reference node, the comparator output will go low, which can be represented by logic 0. So for the ADC, number of comparators that are required can be given as 2 raised to n minus 1. Okay, so this is how we can easily understand how many comparators we can use for designing the A to D converter. So if you want to perform the experiments, what we can do? Now to perform this, we can calculate the voltage drop across each resistors in series, as you can see here, right, and note down on the table below, which is C3, and then next add the connections from the reference nodes A, B, C on your voltage series to each of inverting terminals. You can see here you can connect this one, this one, this one. This is your reference voltage which is constant, and this is your analog voltage. So depending on the value of analog voltage, either our output will be 1 or it will be 0. Now you can connect the output of comparators to encoder, which takes a 3 bit output C1, C2 and C3 from comparators in a figure and encodes that in a 2 bit binary signal A and B for further transmission. This completes the A to D converter. So what we will see is we will see C3, which is a voltage across comparator C3 here, and then we will see the binary value, same way for C2 with a voltage, and we will see the binary value here, we will have voltage across C1, and then we will see the binary value across C1. So we will perform the experiment for different analog voltage. Now you see analog voltage is varied from 0.5, 1.5, 2.5 to 3.5. So we will this is your analog voltage, which is analog signal here, right, and like I said, the reference voltage can be depending on the resistor, it will be constant, and how many comparators you can use? You can use 2 raised to n minus 1 comparators. So let us see how we can design this particular experiment and how we can perform the experiment using the breadboard. So for this experiment, again let me call my TA to show you the details about how to perform the experiment for flash type ADC. Alright, again you have any questions, feel free to ask us, we will respond to you as soon as we can. Till then, let us see how we can perform this experiment.
Now we will see the experiment on flash type ADC. So in Professor's lecture, he has discussed about the working of ADC. Now we will see the theoretical understanding of how exactly the ADC works, and we will also look into the simulation results of the flash type ADC, and we will also see the experiment of flash type ADC, and we will compare the results of all the three. So before going into the theoretical understanding, just recall what professor has discussed. So ADC is nothing but your analog to digital conversion. So the simplest way of converting your analog signal, your real world signal, which will be always in the analog, to a digital, where if you want to do any processing in your microprocessor or microcontroller which is in a digital world, a simplest way of conversion is by using your flash type ADC. So that is why the name itself says that flash, in the sense very fast. So very fastly you can convert your analog value to digital, but the problem or the disadvantages of going with the flash type ADCs are that the complexity of the circuit. Since if you recall the circuit of an flash type ADC, it uses comparators. So when I say comparators, the complete conversion of your analog, the complete conversion or the output of the comparators entirely depends upon the fast of your op amp. And in today's market, if you observe, the comparators with very high conversion, with very high very fast conversion, the comparators are available in the market. So as a result, the speed of the complete conversion depends upon the comparators what we are using and what we are choosing it. So because of that it is very easy to convert your analog to digital, but the problem is that the number of comparators that we have to use in order to convert your analog to digital is entirely depends upon how many number of bits that you are using. Generally speaking, if you recall, if you are using the bits, if you are using some n number of bits, the number of comparators that we require is 2 power n minus 1, right. So suppose if I say I am using 8-bit converter, we require 2 power 8 minus 1, 256 minus 1, 255 number of comparators required, right. So as a result, the complete, if you imagine 255 op amps or 255 comparators, imagine the complete the size of your board. Now if you see the microcontroller, it has an onboard ADCs itself. If you observe the onboard ADCs as well as the microcontroller, the size will be almost equal to your 8-pin operational amplifier, right, or 16 or 17 pin 16 pin operational amplifier, the size. So now how can we do it? If you go with a flash type ADCs, it is very impossible. So because of that complexity, the flash type ADCs are generally used only for low bit conversion. But the cost, as if you observe, the cost of in each comparator itself is very expensive. As a result, 255 comparators will be very expensive. So higher the number of bits that you are planning to convert from analog to digital, higher the cost and higher the complexity and bigger the size of your complete system too. So that is a result, the analog the flash type ADCs are generally used only for the lower bit of conversion. But forget about all the things, first we will understand how exactly this flash type ADCs converts your analog to digital. So if you see the circuit, this is how the circuit looks like. So since basically the circuit whatever we have shown is a 2-bit conversion. So if you recall 2 power n minus 1, so 4 minus 1, 3 comparators are required, that is why we are using 3 comparators. Now if you recall how exactly the conversion process happens, if you recall 2 important things you have to always remember. One is sampling, which is dividing your time domain, and other one is a quantization. Right. If I put it on a graph, so if I say this is time and this is time domain and this is voltage domain, if I say this is your signal, right. So sampling is dividing your time domain, whereas depends upon how many number of bits that you are considering, this complete voltage will be divided into those many number of levels. In this case, since it is a 2-bit, the complete voltage will be divided into 4 levels, right. So 0, 0th level, this is first level, second level, third level. So 0 to 4 levels. the complete voltage will be divided into 4 levels, isn't it? So, depends upon which level this particular voltage are lying, that will be quantized to either 0 0, 0 1, 1 0 and 1 1, right. That means you require to have different levels. So, your complete reference voltage has to be converted into 4 number of levels. That is the reason if you look into the circuit, here we are using different resistors, and the input of the comparator is the one terminal input is completely coming out of the voltage divider circuits. So, that is nothing but these are the references, these are the level references. For example, like say if I consider the reference voltage as a 5 volts, reference as 5 volts, and the input voltage signal is between 0 to 5 volts, in between 0 to 5 volts. So, you should have to divide this complete 5 volts into 4 levels, right. So, in this case if you observe, the resistors are chosen such a way that the each level value will be 1 volt, 2 volt, 3 volt, and above that it will be completely 5 volts. So, that means that, so how do we divide into this? That means this reference voltage is, the first reference is 1 volt, I mean first level the voltage is 1 volt, the second level voltage is 2 volt, this is 3 volt, and more than 3 volts it is completely higher. So, if I want to divide in that way, because it is easy to understand, so we are chosen as resistors such a way that the first one is 2k, 1k, 1k and 1k. So, when we do the voltage divider equation, when you apply voltage divider formula, if I want to know what is the voltage at this point, let us take this as V1, VA1, this is, or VA, this I am taking as VA, VB, sorry, this is VC, this is VB and this is VA. If you look into that, the VC is nothing but reference voltage into the resistance, that is nothing but 1 kilo by sum of resistances. So, 2 plus 1, 3, 4 and 5. So, if you observe that 5k, kk cancel, 5 cancel. So, VC is nothing but 1 volt. So, if you apply the reference of 5 volts, the VC voltage will be 1 volt. So, what about VB? So, 5 into 2 by 5, it is nothing but 2 volts, and here it will be 3 volts, 5 into 3, 1, 2, 3 resistances divided by 5, right. So, it is nothing but 3 volts. So, that means if your voltage is, when you see the output voltages of C1, C2, C3, so that entirely depends upon whether it is high or low, entirely depends upon what is your input voltage, because your references, the negative terminals of your all 3 comparators are already fixed, right. So, this comparator negative voltage will be 3 volts, this will be 2 volts and this will be 1 volt. Now, if you recall how a comparator works, right, if you recall, if your input voltage, when you recall the working of a comparator, the output will become plus VCC if your input voltage, positive input voltage is greater than negative input voltage, then the output will be plus VCC, right. If the negative voltage is greater than positive voltage, then the output will be minus VCC, right. So, if I say if the negative VCC is connected to ground and positive VCC is connected to 5, you will get whenever your negative voltage is greater, you will get a 0 volt, and whenever your positive voltage is greater than the negative voltage, you will get 5 volt. So, which looks like a digital output, right. So, that means you can also get a digital output using a comparator. So, that is why a comparator is a single bit analog to digital converter too. So, if you understand this, if you observe, if you look into the complete circuit, look into the table, for example, like say if your input voltage is 0.5, right. So, now you can understand that this particular voltage is 3 volt, this is 2 volt and this is 1 volt. Now, say my analog voltage is 0.5, right, 0.5. So, what will be the output at C1, C2 and C3? So, if you see that, so this is 0.5, this is at 0.5 volts. So, by understanding the working of a comparator, the positive output voltage, the positive terminal voltage is lower than the negative terminal, right. In this case, the positive terminal voltage is lower than negative terminal. As a result, you will get the output as minus VCC. So, that means 0, right. What about in this case? In this case, this is also at 0.5 volts, this is 12. So, negative voltage is higher. So, again this you will get 0 because I am connecting it to minus VCC as ground. Otherwise, you will get whatever the voltage you are applying at minus VCC, right, or I will say minus VCC, minus VCC, this is also minus VCC. What about this? Minus VCC. So, since I am making minus VCC as 0 and plus VCC as 5 volts, I can say C1, C2, C3 as a binary value as 0, 0 and 0. What about the voltages? Voltages are nothing but minus VCC, minus VCC, minus VCC. Now, what if my input voltage is 1.5? Now, considering my input voltage is 1.5, right. So, that means this 1.5 volts, this is also 1.5 volts and this is also 1.5 volts. Now, if you observe that the positive input terminal of a comparator is higher in op amp 1, the positive input voltage is higher than the negative input voltage. As a result, the output voltage now becomes plus VCC, right. So, this becomes plus VCC. So, even this one, if you see, the positive input voltage of comparator 2 is smaller than the negative input voltage because the reference value is 2 volts here. So, since it is lower than your negative, this becomes minus VCC, right. So, what about here? Even in this case 1.5 is smaller than 3 volts, which is negative terminal voltage is higher. As a result, this still remains at minus VCC. So, that means if the analog input voltage is 1.5 volts, the output from C1 will be 1 in case of binary, because we considered plus VCC as 5. So, if you remember the TTL logic, if the input voltage is greater than 2.5 volts, I can say it as high. So, that is why 1. So, the output C1 voltage will be plus VCC. The binary voltage of C2 is minus VCC, which is nothing but 0. So, this is minus VCC. Similarly, even this is 0 and this is minus VCC. What if it is at 2.5? So, if this is at 2.5 volts, right, this is also at 2.5, this is also 2.5. If you observe that, now the output voltages will be completely different. See, so 2.5, when you consider the first op amp, the positive input terminal 2.5 is higher than the negative input voltage. As a result, you will get an output as plus VCC. What about for comparator 2? When you see the comparator 2, the positive terminal voltage is higher than the negative terminal. Even in this case, you will get an output as plus VCC. What about here? It will be negative terminal voltage is higher, so this will become minus VCC. So, if I write it in the table, I can write it as C1 as 1, but the voltage is plus VCC, C2 is also 1, but the voltage is plus VCC, and C3 is again still 0 minus VCC for 2.5 volts. Now, what for 3.5? For 3.5 volts, if I put 3.5, this will be 3.5 volts, this is also at 3.5 volts, this is also at 3.5 volts, right. So, what will be the output voltages of all the comparators, right. If you see the output voltage 3.5 is higher, so this becomes plus VCC, this also plus VCC. So, and even comparator 3, the positive terminal voltage is higher, this will also be plus VCC. So, that means C1 output is 1, that is voltage is plus VCC, this is also 1, this is also plus VCC, and still this is also 1, this is also plus VCC, right. But if you recall what I said, for 2 bit operation we require 3 comparators, but when I see the output bits are 3, but I need to have a 2. So that means along with this, for this comparator it contains so along with this, if you recall, it contains one more decoder, or it has an encoder which is nothing but demux, right. So if I write a table C1, C2, C3, so for input voltage of I will write it in this way. If you write it as C3, C2, C1 and input voltage of 0.5 volts, I got it as 0, 0, 0, right, and for 1.5 volts I got 1, 0, 0, whereas 2.5 volts 1, 1, 0, whereas 3.5 volts 1, 1, 1. So if you apply encoder, so you will get the 2 bit, 3 bit will be converted to 2 bit, it is nothing but 0, 0, this is 0, 1, this is 1, 0 and this is 1, 1. So finally you will get 2 bits B1 and B0, right. So this is how your flash type of converter is working. So along with a in a flash converter, along with the comparator, it will be connected to an encoder, right. So this is here the complete working of your flash step converter. So as a result, if you see that whenever you are if the input voltage is below 1 volt, it will be in the 0th level, you will get an output as 0, 0. So that means the input analog voltage is converted to digital bits. If your input is between 1 to 2, that means 1.5, that means it is below the second level, it is lying in the first level, so you will get output as 0, 1, right. Now in this case, if the input is 2.5, you will get 1, 0. If input is more than 3 volts, you will get output as 1, 1. So depends upon what resistors that you are choosing here, depends upon what is the reference value that you are choosing here, the complete precision or the resolution of the reference levels is completely depends upon how many number of bits that you are using, what is the reference value that you are using, right. So since it is a 2 bit ADC, the resolution will be really higher. So I mean the resolution value will be higher, that means if your input voltage is below 1 volt, it is very it cannot, if the input voltage is between 0 to 1 volt, the peak value is only between 0 to 1 volt, it is very hard to see the change in the output voltage. So if your input voltages are between 0 to 1 volt, either you have to go with a gain amplifier, and output of the gain amplifier should be connected to your ADC. As a result, the complete levels of your ADC will be completely used, so that the resolution can be increased, or your input signal or your reference voltage value should be connected to the 1 volts, so that between 0 to 1 volts you will have 4 levels, or you have to go with an higher bit ADCs, right. I hope this is clear. Now we will see the simulation in multisim. So this is how the multisim looks like, as we have already seen even in our previous sessions. I am not going to discuss about the complete multisim. So what I am going to do is that one thing is I have to use 3 comparators, right. I can go with an ideal comparator in this case, or you can go with a 3-terminal 5-terminal op amp, connect plus VCC and minus VCC such a way. So anything is fine. So I am going with an ideal comparator, right, and so I need 3 comparators, 1, 2 and 3, and we are using the resistors as the first resistor is 2K, after that 1K, again 1K, 1K, right, and we need one reference voltage, sorry, ground connecting here. So, all should be connected here, this is also here, this is also here, right. So, we need one reference value. So, this is our circuit, we need one reference value. So, this I am considering as a reference, and the reference value is also 5 volts, connecting here and connecting it to here, right. This is, I am naming it as reference VR. Okay. So, the negative terminals are connected 1 to here, this is B C, whereas this is V B and this is V A, right, whereas the positive terminals we are connecting it to input voltage. So, I am taking one more voltage source which is input voltage source. So, V 1 is the input, other terminal should be connected to the ground. So, this terminal should be connected here, this should be connected here, this should be connected here, other terminal of voltage source should be connected to ground. So, I am connecting it here. So, this voltage value is between 0 to 5 volts I am applying. Now, to understand what is the output voltage we get, I will connect one voltage probe here. Okay. So, I will take one resistor, connect here, I will put a probe here, one probe, so just to keep the probe I am placing a resistor, that is not a problem. So, one more probe and the third probe. So, C1 will be in blue color, C2 will be in sky blue color, whereas C3 will be in green color. This you can connect it to ground, not a problem. Now, I will also put some more probes, one here, other one here and other one here, right. So, when I run the system, oh sorry, there is an error, this should not be connected to ground because otherwise it shows shorted. Yeah, let me run. When we see that, so the input voltage applied is 5 volts. So, now if you see so this is V reference into 1 divided by 5. So, you are getting voltage of 1 volt. So, we have chosen a resistors, this R1, R2, R3, R4 resistors such a way that we will get first reference as first level as 1 volt, second reference as 2 volt and third reference as 3 volts. Suppose if you want to equally distribute as 5 by 4. So, we can choose all the resistors as 1k, 1k, 1k. As a result, we will get first level as 5 by 4, second level as 5 into 2 by 4, 5 into 3 by 4. So, in the same sequence. So, we have chosen this 2k because of that reason, so that each level will be 1 volt, easy to understand, right. So, now since this is going to all the negative terminals and V1 which is input voltage I am making it as 0.5, right. When we see because of 0.5, so the positive terminal voltage is higher in all the 3 cases. As a result, this is also the C1 is also at 0, this is also at 0, 0. So, you got C1, C2, C3 as 0, 0, 0, right. So, if you pass through the encoder, you will get 0, 0 as an output. Now, I will make it as 1.5. Now, if you see this value is higher when compared to this value, you got only C1 as 5. 5 volts, whereas this is 0 0. So that means when I look in terms of a digital way, this is 1, this is 0 0. So 0 0 1, when you pass through an encoder, you will get an output as 0 1, right. So this is 2.5, if I make 2.5, see this value is higher, this is also higher, the positive terminals of both U2 as well as U3 op amps are higher. As a result, we got C1 as 5, C2 also 5, and whereas C3 is 0. So when I write it in a digital format, it is 0 1 1. So 0 1 1 pass through an encoder, the corresponding output will be 0 1, right. Suppose if it is greater than 3 volts, so making it as 3.5, we can see 5 5 5. So 1 1 1 passing through an encoder, you will get 1 1. So as a result, we can see the between these levels how the encoder is converting and giving it as a digital value 0 0 0 1 1 0 and 1 1, right. Now we will see the same circuit in a breadboard, and we will see whether we are getting the output voltages as plus VCC and minus VCC too. So in this case, rather than taking a direct comparator, we know that any op amp can be used as a comparator. For the purpose, we are taking LM324. The purpose of using LM324, when you look into the board, when you look into this breadboard, the purpose of having this is LM324, the purpose of using LM324 is that it can be even used in single rail power. So that means the minus VCC, we have seen that minus VCC we will be making it as 0, which will be realistic to that our digital pulse, whereas a plus VCC if you connect it to 5 volts, so since it is 0, whenever your negative terminal is higher than the positive terminal, it goes to 0 directly, so which looks realistic to our digital pulse. So that is the reason we are chosen an LM324, which can be operated with a single power source too. So that is why the negative terminal is connected to the ground, and the positive we are connecting it to plus VCC, which is nothing but 5 volts in this case. And these are the other resistors, right, starting from 2K. So this is the 2K 1K and 1K in series 2K, and whereas another resistor 1K 1K 1K. So the output whatever we take at this point is nothing but your VC. So this is the value. When you look into the screen, so this is nothing but this particular value, right. Whereas this blue line is VB, and whereas this blue line is VA. Okay. So these are connected to all op amps. So this is a quad op amp, so, right. So since this is a quad op amp, you can use all the 3 comparators within single IC, right. So if you see this VC is connected to this particular op amp, and whereas this is connected to this particular op amp stage, whereas this blue line is connected to this op amp stage, right. When we look into all the 3 outputs of op amps, we will understand, right, whether we are getting 5 digital pulse with respect to the input voltage. Now let me switch on the circuit. So if you see the connections of the circuit, so with this channel, so it has a total of 3 channels, 1, 2 and this 3. This one is completely plus 15 and minus 15. Since I am not using plus 15 and minus 15 in this case, I am not going to use this particular port, right. So now if I see here, this is connected to this itself is using as an reference as well as plus VCC to your op amp, because the reference whatever we have considered is also 5 volts, as well as the input voltage we are planning to give it to the op amp is also 5 volts. That is why this particular channel I am using for both reference input, right, which is input to your resistor divider network, as well as input to op amp, and whereas this is your actual input, your input voltage. So let me switch on the circuit. So before switching on, make everything to 0, currents as well as voltage is to 0, and I am switching it on. Now I am changing the voltage of this to 5 volts. Okay. So let me increase little bit of current, and whereas this is my input voltage. So, what I will do is that let me increase a little bit of current and 0.5 volts, see here. So, 0.25, 0.5, that is what the first input voltage that we have considered. Fine adjustment 0.5. So, let me check the output voltage by using a multimeter. I am connecting it to voltage range. So, this is ground, right. Now, the complete input value that is connected to the voltage divider circuit, that is nothing but a reference is phi, right, we can see in the multimeter, right. So, now this resistor and this resistor in series, this resistor and this resistor in series. So, if I see the voltage here, I will start with VC, the VC value is 1 volt, we can see, and the another voltage divider value is 2 volts, another value which is blue color one is 3 volts. That means, we know what is VA, VB, VC, which is passing through your comparator. Now, when we calculate C1, C2, C3, we can see here. So, this is the third comparator or the first comparator if you observe. So, the output voltage in this case is the first pin, right. So, this is also 0, whereas the second one is this one, the output is this, the sixth pin. So, even in this case 7.4 millivolts is what showing in multimeter, 7.4 millivolts is also 0, and whereas the first one, the output, the other comparator output is showing 5.2 millivolt. So, which is 0. So, that means, for the input voltage of 0.5 we are getting the output of C1, C2, C3 as 0, 0, 0. Now, let me increase to 1.5 volts. Right. So, we change it to 1.5 volts. So, if you observe the op amp 1 input which is C1, right. Now, so this is the op amp 1. When you see that this particular portion is op amp 1, so this is the output, and whereas this is the positive terminal, the positive terminal is connected to 1 volt, right. So, here we can see now. If you see this op amp 1, the positive terminal is connected with 1 volt, the negative terminal is connected with 1.5 1, and the negative terminal is this one 1.5 volts. So, the output voltage should be plus VCC, right. Since the plus VCC is connected to 4.9, and when you recall the saturation voltage of your operational amplifier, the saturation voltage will be always lesser than that of your plus VCC. Since it is of 4.9, somewhere approximately 5 volts, right, the VCC value is less, will be lesser than 5 volts. So, somewhere it is showing 3.7. So, if I increase plus VCC value, then even that value will change, right. So, 3.756. So, anything greater than 2.5 will be 1. So, I can say this C1 output is 1. What about C2 and C3? So, C2 in this case is this particular part, this particular portion of op amp. Now, if you observe, this is the positive terminal, sorry, negative terminal, which is coming from voltage divider circuit, which shows you 2 volts, and this is the positive terminal which is coming from input voltage, which we have given it as 1.5 volts here, right. Now, when I see the output voltage, the last pin, so it shows 9.6 millivolt. So, which means that 9.7 millivolts, which means that it is 0. So, that is what we have seen, right. If the input voltage is greater than 1 volt, C1 will be 1, whereas C2 and C3 will be 0. 0, 0, 1 is the output from both all the 3 comparators. When we pass through an encoder, it gives you output as 0, 1, right. Let me change the input voltage to 2.5. So, now the input voltage is 2.5, we can see that. Again we will observe. So, this is the op amp 1 part, this is the input term, positive input terminal, which shows you 2.5. This is the negative input terminal, which is 1 because the reference value is 5 volts. Now, what about the output of C1? It should be 1, observe. So, 3.76 volts, which means 1. Now, this is the second op amp portion. So, what I will be doing is, if you observe, this is your input voltage 2.5, this is the negative input voltage 2, that is the second level value, the output will be 3.7 volt, which means that this is also 1. What about C3? So, C3 portion is here. So, observe, this is the positive pin, which is 2.5. The second one is, the second pin is, sorry, right, the output will be, when you check the output, still it is at 0, 7 millivolt, which means that 0. So, that means for input of 2.5, we got C1, C2, C3 values are 1, 1 and 0. So, when we pass through an encoder, so 0, 1, 1 passing through an encoder will give us 1, 0. Now, let me increase to more than 3. So, anything more than 3. So, since we have chosen as 3.5, let me take it as a 3.5 itself, easy for us to understand. So, observe from first op amp, this is 3.5 positive terminal, negative terminal is 1, sorry, negative terminal is 1. So, what about this value 3.6, which is plus VCC. So, that means C1 is higher. This is also 3.5 input V in positive terminal, this is a negative terminal 2 volt, the output is 3, this is also plus VCC. When it comes to op amp 3, the output is even 3.75, which is also 1. So, that means we understood that when the input voltage is greater than 3 volts, which is in the final level, so we will get an output C1, C2, C3 as 1, 1 and 1 are nothing but VCC plus VCC and plus VCC and plus VCC. So, when we represent in digital way, so it is nothing but 1, 1, 1. When we pass through an encoder, input of encoder 1, 1, 1, the output of encoder output will be 1, 1. So, as a result we will get an output as 1, 1. So, that is how this flash type ADCs of 2-bit converter is working. So, I hope this is clear.
Now, this is the flash DAC, but if you flash ADC, but if you want to understand the another kind of ADC, which is a dual slope ADC, let us see how it works. So, a dual slope ADC is a common in digital voltmeters and other type of measurement instruments. A block diagram of dual slope ADC is shown right over here, where it consists of the analog input signal, there is a switch, there is a integrator or ramp generator, and there is a comparator with a control logic. There is a switch which is connected to the to this block, right, through a control logic, and then you have a clock you have a counter, you have latches, and finally you have the binary output. So, this is a block diagram of dual slope ADC. Suppose people ask, or if in exam you are asked what kind of dual slope ADC block diagram looks like, you can draw this very quickly. Assume that the counter is reset and the integrated output is 0. Okay. So, if the counter here is reset, right, counter is reset and your here counter is reset and your integrator output is 0, right. So, a positive input voltage is applied to the input through switch. So, here we are connecting switch to the positive input voltage, and then since the inverting input of A1 is at virtual ground, and assuming that V in is constant for a period of time, there will be a constant current through the input resistor and through capacitor, correct. So, it will be a constant current through input resistor and capacitor. When you connect these 2 plus V in, capacitor will start charging linearly because the current is constant, and as a result there will be a negative going linear ramp on the output A1, correct. Now, when the counter reaches a specified count, it will reset and the control logic will switch back the negative reference voltage to input of A1. In that case, what will happen? At this point, capacitor is charged to negative voltage proportional to the input analog voltage. So, now the capacitor discharges linearly because of the constant current from minus V reference. So, now the capacitor has to discharge and have a constant slope that is independent of charging voltage. So, one is capacitor charges, then the counter resets and the capacitor starts discharging. As the capacitor discharges, counter advances from its reset state. The time it takes from capacitor to discharge from 0 depends on the initial voltage minus V. When it reaches A1 reaches 0, A2 switches to low state, right, because A1 reaches to 0, A2 will reach to low state, and disables the clock of the counter, which is if it is low, the clock will be disabled, and if that is the case, the binary count is less, thus completely one conversion cycle. The binary count is proportional to voltage V in. Now, this whole process is illustrated right over here, right, where initially the capacitor is charging when your counter up to n and then it resets, and then it is sent back. It when it is connected to plus V in, it is charging. When it is connected to ground, then at some point it, because of the when the reset signal is sent, it will start discharging, capacitor will start discharging. This will cause the change in the output signal. Now, if you have understood the flashed and dual slope ADCs, then let us see successive approximation ADC. Successive approximation ADC, the block diagram is shown here, where it has a digital to analog converter, it has a SAR, it has a digit and clock, and it has the serial binary output. It is connected, the signal which is a digit connected is to the output of the comparator, and we have a parallel binary output from D0 to D3. Now, the input bits of DAC are enabled only one at a time, starting with the most significant bit. Okay. And as each bit is enabled, the comparator produces an output that indicates whether the input signal voltage is greater than or less than the DACs. So, you understand this thing, if the V out here and the initial input here. So, if it is more than DAC or less than EAC, we can easily see with the help of comparator. If the signal input is more than DAC, then we can have a higher bit. If the signal input is less than VAC, we can have a lower bit, right. So, the input of the DAC are enabled one at a time with MSB. At each bit is enabled, comparator produces an output that indicates whether input is greater or less than the output of DAC. If the DAC output is greater than input signal, the comparator output is low, causing the bit to the register to reset, right. So, we send here a digit called reset. Now, if this DAC output is less than input signal, then bit 1 is retained in the register. Now, this is of course a register which is shown here, and the system does this with the first MSB first, and then next right of they start with MSB and then this one and then this one, and finally comes to the LSB. Okay. After all the bits in DACs are tried, the conversion cycle is completed. So, this is V out of 8 bit volts for 2 raised to 3. You can see here, assume that DAC following characteristics, you can very clearly see plus 5.1 volt, plus 5.1 volts is given. Now, if you have here 8, then 8 volt is greater than 0. So, low is sent, right. So, now it is sent here. So, when you apply a clock, you have 1 0 0 0, but if you have for 6 volts, right, then what will happen? here is still is more than 5.1. So, again a low is applied and you have if you send the signal, then it will be 0 1 1 0, right. So, 1 1 0 will be the value. Same way if you go for 4 volts, then in that case 4 volts is less than 5.1 volts, that is why it will be high bit, and you can have here 0 and then 1 and 0 and 0. This will be in your register, which is the value you have to keep. Now, in this case, if you see if there is a low value, then you have to reset this value. If there is a low value, you have to reset this value, but if there is a high value, then you can keep this value. Same way here 5 volts is less than 5.1 volt, you can keep the last significant bit, which is or least significant bit, which is 2 raised to 0, right. So, 1 volt for 2 raised to 0 bit we can retain here, right. 2 volts for 2 raised to 1 bit we can see here, and similarly. So, it is very easy to understand the DAC ADC characteristics and DAC characteristics. Now, this is how the operation works. So, just to look at the slides in detail, you can see very clearly. Let us take one example or let us take this example where step 1 you have 2 raised to 3 ms bit, which is your most significant bit, and the output of DAC is 8 volt. Since this is greater than 5 volts, the output of the comparator is low, causing the MSB of SAR, which is successive approximation register, to reset to a 0. Now, step 2 is 2 raised to 2, which is bit 1. So, output of DAC is 4 volts, which is less than 5.1 volt. In that, the comparator switches to high, causing this bit to retain in SAR. Similarly, step 3, if it is 2 raised to 1, which is 1 volt, then output of DAC is 6 volts. Since this is greater than 5 volt, the output of comparator switches to low. So, it is very easy, right. If it is more or less, that is what we are comparing. Nothing so difficult in this particular ADC. Now, the final one would be sigma delta ADC. So, what exactly sigma delta ADC means? This method is based on delta modulation, where difference between two successive sample is quantized. The output of delta modulator is single bit stream, where the relative numbers of ones and zeros indicate the level of amplitude, right. So, how many zeros are there, how many ones are there, and the number of ones over a given number of clock cycle establish the signal amplitude during the time interval. Now, here the maximum number of ones corresponds to maximum positive input voltage, and number of ones equal to 1 half the maximum corresponds to input voltage 0, right. So, 1 half will correspond to 0, only 1 will correspond to high. Number of 1 correspond to maximum negative input voltage. This is illustrated in simplified way in this particular figure, as you can see here. 20481, 40961, these are all zeros. When zeros, it is minus negative, if it is 1 it is plus, if it is in between then it is considered as 0. So, if you see this particular ADC, right, which is our sigma delta ADC, then this is the block diagram where you have the integrator, a quantizer, n bit counter, latch, and output of the 1 bit quantizer is fed back to the 1 bit DAC, which is sent to the summing point, where the summing point will look at the signal sent by 1 bit DAC and analog input signal, and the error is fed to the integrator. So, this is what is written over here, and a different signal output of the sum is integrated, and 1 bit DAC increases or decreases, the number of 1 depends on the different signal. This action attempts to keep the quantization signal, that is feedback, equal to incoming analog signals. The single bit data stream is converted to as a series of binary codes. The counter counts ones in the quantized data stream and code in the counter that represent the amplitude of analog signal for each interval. So, the point is the most easiest way of understanding DAC or ADC is when you use it. Until you use it, you guys will not know how to operate these ADCs and DACs. Okay. So, what I think what we have learned in this particular module is what kind of ADCs are there, and we are just if you have really see, we are kind of run through that ADCs. The reason is that we have to use these ADCs. The detail of how the ADCs are operated is good to understand, but how you can use it is more important. Alright. So, I leave it on you how you read it further, how you understand it further. If you are confused, do ask me, anytime you can ask me, but if you know how and where to use ADCs and DACs for a signal conditioning system, that is where the real application lies in. because when you design an electronic conditioning system, you need to know what kind of circuits you have to use, right. At what point your ADC will come, at what point your DAC will come, at what point your filters will come, at what point your amplifiers will come, at what point your integrator and comparators will come, at what point your sine wave and this kind of frequency generator signals will come, at what point you have to interface your sensors to your electronic conditioning system, and at how you can convert this data to a display. So, this everything in some sort, when you bring it together, you can design a complete system. And through this particular modules, what I have tried is to help you out or to share with you how to apply or use operational amplifier in real life scenarios, in the practical applications, and in that, when you see the block diagram, when you further go and see the circuit diagram, then you will see that where exactly this kind of circuits are used. Okay. So, you just go through it once again, ADCs and DACs, and you prepare it well. We will have lot of experiment class where you will be looking at lot of experiments, including the simulation and the experimentation, right. I have designed all the experiments for you guys. So, just look at it, and even in that portion, if you are stuck, if you are if you have any doubts, feel free to ask me, right. Till then, you take care.